In this video I'm going to explain how to use solve IVP to solve ordinary differential equations. So here I've got the usual imports, numpy and pypot, but we're also going to import another thing, this from scipy.integrate import solve IVP. And so that gives us this solve IVP function which we can use to solve differential equations. So standard thing, we're going to be solving something of the form dy by dt is f of ty with some range of values of t. And as well, let's just initially, that's just the absolutely simplest example. Okay, so let's just do fty as y, so we're just solving y dot equals y. The solution, of course, is just an exponential. So we're going to use the solve IVP to solve it, and we can hover over there to see what information we need to provide. So the first thing we need to provide is the function itself, which is just f. And the second thing we need to provide is this thing called t-span. So that's going to be the pair of numbers a and b, where we're solving it. Let's say solve it from 0 to 2. Then the next thing is the method. The default method is called RK45, and we're going to use the default method, so we're not going to bother with that. But before that, though, we've got to do y0. Y0 is the initial thing, initial values. So we're going to take initial value to be 1. But for solve IVP is kind of set up to do things where your y. I mean, here in this case, y is just going to be a number. Y could be a vector. You can do vector differential equations, and then you have the time derivative of a vector being given by some vector function. In order to kind of handle that, this solve IVP thing requires that we provide a kind of vector here. So the vector, instead, it's just going to be like a vector of length 1, but we are not allowed to just write 1. We have to write it in square brackets as kind of being like a vector. Okay. Then the next argument is the method. We're just going to use the default method, so we're not going to specify anything there. The next thing is t-eval. Those are the times at which we want to know the solution. So we want to know the solution sort of between 0 and 2, but we also want to know, of course, if we're going to plot the solution, we need to know at a bunch of points between 0 and 2. So here we have to tell it which points we want to plot. So we're going to do so let's say 101 points starting at 0 and ending at 2. But notice, we missed out an argument. We missed out the method. The way arguments work in Python, as soon as you skip one argument, then you actually have to provide the names for any further ones. So we can't just put that in there by itself. We have to kind of say that this is the t-eval argument. And then there's a bunch more things that we could in principle put in, but we're not going to bother. Okay. So now it's given us this solution. So what is this solution? I mean, you might think that we're just going to say plot sol or something, but plt.plot sol. But it doesn't like that. That's because the information is packaged within this sol in a way that we need to understand. So you could just look up the documentation. Another thing we can do is we can just do dir sol. That kind of tells us what there is. Okay, so so you've got all this business here. Sol. There's a t and the y and things. So that kind of means that we can do sol.y. And we see that sol.y is kind of this big array here. This is the kind of main thing that we're interested in, the actual values of y, and we get that as sol.y. There's also sol.t. Sol.t is just the array of times. So that means that if we want to plot it, we just do plt.plot, and there's the times against the y values. But then okay, so that didn't work, and let's just check why that didn't work, let's go back and check again about sol.y. Okay, sol.y is you've actually got 2 square brackets, and we do sol.y.shape. You see that this is actually it's like a row vector of shape 1, 101. So the upshot of that is just we have to write sol.y.0 instead of sol.y. Okay. So that's this is how we get the actual solution out of the result of this solve IVP thing, and there we are. We've plotted it. And that wasn't a terribly interesting example. We'll do a more interesting example. Okay, so we're going to do a plus np.sine so we got so now we're going to have an extra parameter that's called a, and we're going to then our derivative is going to be a plus sine pi t plus sine pi x, or sorry, sine pi y. So then, and certainly note, here we said sol.y. Now, and we've called the variable here, we've called it y, so everything fits together. But quite often, you might, in your own workings, you might use a different variable name, and you might have a different name for the argument here. It might be called x instead of y or something, or p or whatever you like. But when you try and get the answer out of this sol thing, you always have to call it sol.y. That's just how it works, right? Even if you're using a different name elsewhere. Okay. So here's this function, and so we're going to do again. I think so let's try and solve this. We're going to solve it in the range t is 0 to 100. And I'm going to start with y equals 0. And for this example, I need quite a lot of accuracy, so I'm going to put in lots of extra points. So now I'm getting an error message. Why is that? Well, so I go and find the error, and it says f is missing one required positional parameter a. Right. So we introduced this parameter a, and I didn't tell you what it was. So the way I have to tell you what it is, I'm going to have to put in an extra thing here called args, and we're going to take let's take a to be 0.7. But the args has to be provided as a tuple, and remember, tuples of length 1, you have to put in the comma. So we're going to put in args as 0.7 comma to make that into a tuple. Okay, let's get rid of this, and let's plot it. Okay, so so that's kind of a slightly strange function. In fact, you get some more things. So we'd like to sort of plot this. That was a particular value, 0.7, we took for a. I'd like to show you how it changes when we change the value of a. So to do this kind of in a more systematic way, let's actually define a function. Okay, so we're going to do. Okay, so we're going to define a function to show the solution for a particular value of a, and then we're going to so again we'll take maximum value of t to be 100, and the evaluation points we're going to take let's put in 2000. The initial value we'll take to be 0. So I'm going to use the function f that we've got already. Then we have to do the t span, which is going to be from 0 to t max. Then our y naught, which is going to square bracket x naught for that. And then the method, which we're going to ignore. Oh no, actually we're not going to ignore the method, because so for the phenomena that I want to show you, it's quite important that we make we solve this thing extremely accurately. So we're going to use the fanciest available method, which is called L-soda, and then we're going to specify the evaluation points, and then the arguments. The extra argument is this A that we had here. Again, have to convert it to a tuple of length 1. And then we're also going to ask for very high accuracy. So there are these two different parameters. I'm not going to explore exactly what's the relationship between them. We're just going to make them both very small. Okay, that's called absolute tolerance and relative tolerance. We're going to set both of them to be 10 to the minus 10. So that should give us a, I'm not going to be terribly precise or careful about exactly how accurate this we're going to end up with our solution being, but that should be pretty accurate. Then we get a plot. But we're also going to, let's put in a label. So we're going to do, we're going to put a label which tells us what's the value of A. Okay, so we're going to say, so we put the A in curly brackets and we do colon 0.3f. That means we'll want to see it to 3 decimal places. And then we show the legend. Okay, so so we showed it 0.782. Okay, what have we got wrong here? Okay, again, same business that I forgot. We need to do 0. Yes, it were. Okay, so that's showing the same thing again with A is 0.782. Let's try it at A is 0.784, and you get these kind of wiggly step things. And we change it just a little bit more to 788. Now we get lots more steps. So that's kind of quite weird behavior. So maybe we should like to see those three things next to each other. So let's just do that. So what we'll do is we'll put in an extra argument here. We'll put in an ax as an argument. And then we're going to do ax.plot here and ax.legend. Okay. So now what we're going to do. Oh, yeah, so, okay, so we're going to make a kind of 1 by 3, 3 by 1 grid of plots. And then we're going to show 0.782 on the first one. .784 there and 0.788 there, so that's okay. But let's make it wider. Okay, so there we see how the plot changes as we increase A from just by this very small amount from 0.782 up to 0.788. We get a really rather radical change in the behavior of the function. And that will do for that example.